Hello viewers, now I am discussing problem number 7 and 8 on Picard's existence and uniqueness theorem. Today's first problem is prove that the continuity of f of xy is not enough to guarantee the uniqueness of the solution of the initial value problem dy divided by dx is equals to f of xy equals to root of mod y under the boundary condition y0 equals to 0. Here given IVP is dy dx equals to root of mod y y0 equals to 0. Here f of xy is continuous for all values of y. Solving one, we get y equals to x square divided by 4 when x greater than 0 and minus x square by 4 when x less than 0. And another solution is y0 equals to 0, that is y equals to 0 when x equal to 0. And also here two cases may arise. Case 1, y greater than 0. When y greater than 0, we get y equals to x square by 4, and here also x is positive. And case 2, y less than 0, y equals to minus x square divided by 4 when x is negative. Now we show that Lipschitz condition, that is mod of f of x comma y2 minus f of x comma y1 less or equal to k into mod of y2 minus y1. This is equation number 2. It does not hold good in any region which includes the line y equals to 0. We take y1 equals to 0 and y2 is a positive number, that is y2 greater than 0. Then mod of f of x comma y2 minus f of x comma y1 divided by mod of y2 minus y1 equals to mod of f of x comma y2 minus f of x comma 0, because we take y1 equal to 0 divided by mod of y2 minus 0. Okay, thus f of x comma y2, that is root over y2 since y2 greater than 0. For this reason here we get f of x comma y2 equals to root of y2, and mod of y2 is mod of y2. This equals to 1 divided by root of y2, as y2 is positive number. Now from 2 we get, from 2, that is from this we can write mod of f of x comma y2 minus f of x comma y1 divided by mod of y2 minus 1 less or equal to k, and this is equation number 3. This shows that the quantity on LHS of 3 can be made as large as if we choose y2 is sufficiently small. Okay, this violates 3 because the quantity on LHS of 3 should not exceed a fixed. Hence, this violates 3 because the quantity on LHS of 3 should not exceed or a fixed a fixed or given constant k, because here k is fixed. But the quantity on LHS of 3 can be made as large as if we choose y2 is sufficiently small. That is, if we choose y2 is sufficiently small, this is varies from y2 greater than 0. Okay, hence this is not a proper sufficient condition, because here k is a fixed number, and this violates 3 because the quantity on LHS of 3 should not exceed a fixed or given constant k. Okay, so this completes the proof, because here let us show that the given function is not enough to guarantee a uniqueness of the solution. Okay,
E is.
Now I am discussing problem number 8. For the initial value problem, dy dx equals to e to the power y 0 equals to 0. Find the largest interval mod x less or equal to a in which the Picard's theorem guarantees existence of a unique solution. And next problem, for the initial value problem, dy dx e to the power y 0 equals to 0. Here find the largest interval mod x less or equal to a in which the Picard's theorem holds. First problem, in which the Picard's theorem guarantees the existence of a unique solution, and second problem, in which the Picard's theorem holds. Okay. Here the condition of boundedness of f of xy, that is mod of f of xy less or equal to m for mod of y minus y0 less or equal to m into a. This is boundary condition, the condition of boundedness of f of xy. Since f of xy equals to dy dx equals to e to the power y, this implies that e to the power y less or equal to m. With these conditions, for y minus 0, this mods less or equal to m into a. Here y0 equals to 0 by the given condition. Now let y1 and y2 lie in the range mod y less or equal to ma, and also let y1 is less than y2. Now using mean value theorem, we get f of x comma y2 minus f of x comma y1 equals to y2 minus y1 del f del y with points y equals to y bar. Thus we get e to the power y2 minus e to the power y1 equals to y2 minus y1 del y e to the power y with points y equals to y bar, where y bar lies between, here y bar lies between y1 and y2, that is y1 less than y bar less than y2. This implies e to the power y2 minus e to the power y1 less or equal to, since this is less or equal to m, hence e to the power y2 minus e to the power y1 less or equal to m into y2 minus y1, using 1, which shows that the function e to the power y satisfies the Lipschitz condition. Okay. Our next problem, that is problem number B. Again the inequality e to the power y less or equal to m will be satisfied for all values of y such that mod y less or equal to ma. And in this case, let us assume that mod y equals to ma, that is y equals to ma. Hence e to the power ma, since y equals to ma, hence e to the power ma less equal to m. Taking logarithm on both sides, ma less or equal to log e power e base m, and a less or equal to log e base m divided by m. Now let this is equal to s, ds divided by dm, and we get this term, and d2s divided by dm2 is equals to this term. Since we know that for extremity ds divided by dm equals to 0, and thus we get m equals to e. Since our target is to find the maximum value of s, okay, so we calculate ds divided by dm and d2s divided by dm2, and for extremity we know ds divided by dm equals to 0, and thus we get m equals to e, and this point that is m equals to e, d2s divided by dm2 is equals to minus 1 divided by e cube, which is less than 0, since e lies between 2 and 3, and actual value of E is 2.718, which is maximum for M equals to, that is 2.718. Hence, uniqueness theorem of the given initial value problem gives mod x less equal to a, where a is equals to 1 by e, since a less equal to log e power m equals to e, that is 1, and m equals to e, that is a is equals to 1 by e, and the value of e is 2.718, that is 1 divided by 2.718 is equals to 0.308. Hence the required largest interval is mod x less or equal to a, and we get here the value of a is 0.308. okay, and here mod x less or equal to 0.308. okay, I will also discuss problem number 9 and 10 on Picard's theorem. Thanks for watching.